Fluorite is the mineral form of calcium fluoride, Ca2. It belongs to the halide minerals. It crystallizes in isometric cubic habit, although octahedral and more complex isometric forms are not uncommon. Fluorite is a colorful mineral, both in visible and ultraviolet light, and the stone has ornamental and lapidary uses. Industrially, fluorite is used as a flux for smelting, and in the production of certain glasses and enamels. The purest grades of fluorite are a source of fluoride for hydrofluoric acid manufacture, which is the intermediate source of most fluorine-containing fine chemicals. Optically clear transparent fluorite lenses have low dispersion, so lenses made from it exhibit less chromatic aberration, making them valuable in microscopes and telescopes. Fluorite optics are also usable in the far ultraviolet range, where conventional glasses are too absorbent for use. History and etymology. Fluorite derives from the Latin noun fluor, meaning a stream or flow of water. In verb form this was fluor or fluor, meaning to flow. The mineral is used as a flux in iron smelting to decrease the viscosity of slags. The melting point of calcium fluoride is 1676 K. The term flux comes from the Latin noun fluxus, a wash or current of water. The mineral fluorite was originally termed fluorspar and was first discussed in print in a 1530 work Bermanis. Sideri Metallica Dialogus Bermanis, or a dialogue about the nature of metals, by Georgius Agricola, as a mineral noted for its usefulness as a flux. Agricola, a German scientist with expertise in philology, mining, and metallurgy, named fluorspar as a neo-Latinization of the German fluorspat from flussen, spat. In 1852, fluorite gave its name to the phenomenon of fluorescence, which is prominent in fluorites from certain locations, due to certain impurities in the crystal. Fluorite also gave the name to its constitutive element fluorine. Presently, the word fluorspar is most commonly used for fluorite as the industrial and chemical commodity, while fluorite is used mineralogically and in most other senses. Structure. Fluorite crystallizes in a cubic motif. Crystal twinning is common and adds complexity to the observed crystal habits. Fluorite has four perfect cleavage planes that help produce octahedral fragments. Element substitution for the calcium cation often includes certain rare earth elements, such as yttrium and cerium. Iron, sodium, and barium are also common impurities. Some fluorine may be replaced by the chlorine anion. Occurrence and mining. Fluorite is a widely occurring mineral that occurs globally with significant deposits in over 9,000 areas. It may occur as a vein deposit, especially with metallic minerals, where it often forms a part of the gangue and may be associated with galena, sphalerite, barite, quartz, and calcite. It is a common mineral in deposits of hydrothermal origin and has been noted as a primary mineral in granites and other igneous rocks and as a common minor constituent of dolostone and limestone. The world reserves of fluorite are estimated at 230 million tons, with the largest deposits being in South Africa, Mexico and China. China is leading the world production with about 3 Mt annually, followed by Mexico, Mongolia, Russia, South Africa, Spain and Namibia. One of the largest deposits of fluorspar in North America is located in the Burin Peninsula, Newfoundland, Canada. The first official recognition of fluorspar in the area was recorded by geologist J.B. Jukes in 1843. He noted an occurrence of galena, or lead ore, and fluorite of lime on the west side of St. Lawrence Harbor. It is recorded that interest in the commercial mining of fluorspar began in 1928, with the first ore being extracted in 1933. Eventually at Iron Springs Mine, the shaft reached depths of 970 feet. In the St. Lawrence area, the veins are persistent for great lengths and several of them have wide lenses. The area with veins of known workable size comprises about 60 square miles. cubic crystals up to 20 centimeters across have been found at Delnogorsk, Russia. The largest documented single crystal of fluorite was a cube 2.12 meters in size and weighing 16 tons. Blue John. One of the most famous of the older known localities of fluorite is Castleton in Derbyshire, England, where, under the name of Derbyshire Blue John, purple blue fluorite was extracted from several mines or caves. During the 19th century, this attractive fluorite was mined for its ornamental value. The mineral Blue John is now scarce, and only a few hundred kilograms are mined each year for ornamental and lapidary use. Mining still takes place in Blue John Cavern and Treat Cliff Cavern. Recently discovered deposits in China have produced fluorite with coloring and banding similar to the classic Blue John stone. Fluorescence. George Gabriel Stokes named the phenomenon of fluorescence from fluorite in 1852. Many samples of fluorite exhibit fluorescence under ultraviolet light, a property that takes its name from fluorite. Many minerals, as well as other substances, fluoresce. Fluorescence involves the elevation of electron energy levels by quanta of ultraviolet light, followed by the progressive falling back of the electrons into their previous energy state, releasing quanta of visible light in the process. In fluorite, the visible light emitted is most commonly blue, but red, purple, yellow, green and white also occur. The fluorescence of fluorite may be due to mineral impurities, such as yttrium and ytterbium, or organic matter, such as volatile hydrocarbons in the crystal lattice. In particular, the blue fluorescence seen in fluorites from certain parts of Great Britain responsible for the naming of the phenomenon of fluorescence itself, has been attributed to the presence of inclusions of divalent europium in the crystal. One fluorescent variety of fluorite is chlorophenine, which is purple in color, and fluoresces brightly in emerald green when heated or exposed to ultraviolet light. The color of visible light emitted when a sample of fluorite is fluorescing depends on where the original specimen was collected, different impurities having been included in the crystal lattice in different places. Neither does all fluorite fluoresce equally brightly, even from the same locality. Therefore, ultraviolet light is not a reliable tool for the identification of specimens, nor for quantifying the mineral in mixtures. For example, among British fluorites, those from Northumberland, County Durham, and eastern Cumbria are the most consistently fluorescent, whereas fluorite from Yorkshire, Derbyshire, and Cornwall, if they fluoresce at all, are generally only feebly fluorescent. Fluorite also exhibits the property of thermoluminescence. Color. Fluorite is allochromatic, meaning that it can be tinted with elemental impurities. Fluorite comes in a wide range of colors and has consequently been dubbed the most colorful mineral in the world. Every color of the rainbow in various shades are represented by fluorite samples, along with white, black, and clear crystals. The most common colors are purple, blue, green, yellow, or colorless. Less common are pink, red, white, brown, and black. Color zoning or banding is commonly present. The color of the fluorite is determined by factors including impurities, exposure to radiation, and the absence or voids of the color centers. Uses. Source of fluorine and fluoride. Fluorite is a major source of hydrogen fluoride, a commodity chemical used to produce a wide range of materials. Hydrogen fluoride is liberated from the mineral by the action of concentrated sulfuric acid. Ca2 plus H2SO4 Ca4 plus 2HF. The resulting HF is converted into fluorine, fluorocarbons, and diverse fluoride materials. As of the late 1990s, 5 billion kilograms were mined annually. There are three principal types of industrial use for natural fluorite, commonly referred to as fluorspar, in these industries, corresponding to different grades of purity. Metallurgical grade fluorite, the lowest of the three grades, has traditionally been used as a flux to lower the melting point of raw materials in steel production to aid the removal of impurities, and later in the production of aluminium. Ceramic-grade fluorite is used in the manufacture of opalescent glass, enamels and cooking utensils. The highest grade, acid-grade fluorite, accounts for about 95% of fluorite consumption in the U.S., where it is used to make hydrogen fluoride and hydrofluoric acid by reacting the fluorite with sulfuric acid. Internationally, acid-grade fluorite is also used in the production of alpha-3 and cryolite, which are the main fluorine compounds used in aluminium smelting. Alumina is dissolved in a bath that consists primarily of molten Na3 alpha-6, alpha-3, and fluorite to allow electrolytic recovery of aluminium. Fluorine losses are replaced entirely by the addition of alpha-3, the majority of which will react with excess sodium from the alumina to form Na3 alpha-6. Niche uses lapidary uses natural fluorite mineral has ornamental and lapidary uses. Fluorite may be drilled into beads and used in jewelry, although due to its relative softness it is not widely used as a semi-precious stone. It is also used for ornamental carvings, with expert carvings taking advantage of the stone's zonation. Optics in the laboratory. Calcium fluoride is commonly used as a window material for both infrared and ultraviolet wavelengths, since it is transparent in these regions and exhibits extremely low change in refractive index with wavelength. Furthermore, the material is attacked by few reagents. At wavelengths as short as 157 nanometers, a common wavelength used for semiconductor stepper manufacture for integrated circuit lithography. The refractive index of calcium fluoride shows some nonlinearity at high power densities, which has inhibited its use for this purpose. In the early years of the 21st century, the stepper market for calcium fluoride collapsed, and many large manufacturing facilities have been closed. Canon and other manufacturers have used synthetically grown crystals of calcium fluoride components in lenses to aid apochromatic design, and to reduce light dispersion. This use has largely been superseded by newer glasses and computer-aided design. As an infrared optical material, calcium fluoride is widely available and was sometimes known by the Eastman Kodak trademarked name, IRTRAN3. Although this designation is obsolete, fluorite has a very low dispersion, so lenses made from it exhibit less chromatic aberration than those made of ordinary glass. However, naturally occurring fluorite crystals without optical defects were only large enough to produce microscope elements. With the advent of synthetically grown fluorite, it could be used instead of glass in some high-performance telescopes and camera lens elements. Its use for prisms and lenses was studied and promoted by Victor Schumann near the end of the 19th century. In telescopes, fluorite elements allow high-resolution images of astronomical objects at high magnifications. Canon Inc. produces synthetic fluorite crystals that are used in their more expensive telephoto lenses. Exposure tools for the semiconductor industry make use of fluorite optical elements for ultraviolet light at wavelengths of about 157 nanometers. Fluorite has a uniquely high transparency at this wavelength. Fluorite objective lenses are manufactured by the larger microscope firms. Their transparence to ultraviolet light enables them to be used for fluorescence microscopy. The fluorite also serves to correct optical aberrations in these lenses. Nikon has previously manufactured at least one fluorite and synthetic quartz element camera lens for the production of ultraviolet images. Konica produced a fluorite lens for their SLR cameras, the Hexanone 300mm f6.3, source of fluorine gas in nature. In 2012, the first source of naturally occurring fluorine gas was found in fluorite mines in Bavaria, Germany. It was previously thought that fluorine gas did not occur naturally because it is so reactive and would rapidly react with other chemicals. Fluorite is normally colorless, but some varied forms found nearby look black and are known as fetid fluorite or antozonite. The minerals, containing small amounts of uranium and its daughter products, release radiation sufficiently energetic to induce oxidation of fluoride anions within the structure to fluorine that becomes trapped inside the mineral. The color of fetid fluorite is predominantly due to the calcium atoms remaining. Solid-state fluorine 19 NMR carried out on the gas escaping the antozonite revealed a peak at 425 ppm, which is consistent with F2.